Hello, this is Gnana Prasanna Kanipakam. My research paper presentation is on false data injection attacks induced sequential outages in power systems. It was written by Leon Shi, Xion Liu, Zui Li, and Yufeng Wan. Introduction. Power grids are more vulnerable to cyber attacks. With the evolving smart grid devices and increasing integration of communication technologies, today's power grids are more prone to cyber attacks. In recent years, the power grids fell victim to cyber attacks in different countries. For example, the 2015 Ukraine power grid, in which attackers remotely opened substation breakers and caused power outage, and the cyber attack in Israel's electric grid on a winter peak day of 2016 is another one. Cyber attack can also cause denial of service in power system operations. Promoting effective protection strategies against cyber attacks is vital to ensure the grid security. So, it is necessary to analyze the mechanism and impact of the cyber attacks. Background on paper. The literature has revealed the increased risk of the false data injection attacks. Based on the attacker's goal, false data injection attacks can be implemented in the following ways. First, attacks against state estimation by introducing arbitrary errors into state variables while bypassing the bad measurement detection. The second one is topology attacks. These attacks can mislead the control center with an incorrect real-time topology. The next one is attacks on the economic side for increasing the operational cost or loss or gaining illegal profit from power markets. And the next one is attacks against smart grid applications. For example, phasor measurement unit, the supervisory control and data acquisition, SCADA. And recent works analyzed the vulnerability of power grids and revealed the potential of physical attacks to trigger sequential outages or even to initiate cascading failures. In these attacks, the attacker targets at multiple critical components in order to impose a serious contingency which serves as an initial contingency that triggers subsequent failures. This motivates research in this paper. Background on paper continuation. Besides that, past studies also investigated the system vulnerability regarding the outages triggered or aggravated by malicious attacks. The cyber physical coordinated attack. This attack allows the attackers to firstly launch a physical attack to cause branch outages, then use a cyber attack to mask and exacerbate the outages, causing larger damages to the grid. And the next one is FDI attack masking outage. This was examined and in which the attacker masks the existing line outages to affect the operator's visibility on this fault so that appropriate mitigation measures will not be taken promptly, which leading to larger damages to the system. And the next one is the sequential attacks. This attack showed that the attacker is capable of identifying an optimal cyber attack sequence on system components. The attack imposes a much larger damage or needs less attacking resources than a concurrent attack. Conceptual methodologies. In recent days, cyber attack is recognized as an emerging risk in smart grids. In this paper, it is going to reveal a potential link between data attack and physical consequences and analyzed how the attacker can launch a malicious data attack to trigger sequential outages and thus impose large damages to the grid. In this attack mechanism, the attacker constructs an optimal false data injection attack to intentionally trigger a targeted branch outage sequence that trips multiple branches and then leads to subsequent failures. The studied attack mechanism integrates constructing an optimal data attack and identifying critical lines and imposes a substantial security impact with a high chance of occurring. And finally, simulations on the IEEE 118 bus system verify that the introduced attack mechanism and highlight the risk of such attacks in today's smart grids. Focus of the study. In this study, we analyze the mechanism of triggering sequential outages by false data injection attacks. This analysis builds the link between cyber attacks and cascading consequences in power grids. In this study, we refer data attack as the sequential outage attack. The main focus of this study is to reveal the mechanism of an sequential outage attack. This is a special class of false data injection attacks, which can exploit by an attacker as a tool to trigger sequential outages by overloading multiple branches above their tripping thresholds in a short time, where corrective actions may not be possible. In reality, sequential overloads and outages are the most common causes of blackouts in power systems. Examples: in 2003 Northeast blackout and in 2011 Southwest blackout. Main contributions. The main contributions of this paper are threefold. First, this paper reveals a system vulnerability and identifies a high-risk link between false data and initial contingency of sequential outages in power systems. Here, they analyze the mechanism that the attacker can implicitly identify the targeted initial contingency as a system weak point when designing false data and leveraging such weak point to implement data attack to impose large physical damages to the system. Next, a bi-level model. A bi-level model is proposed to perform a quantitative analysis to fully investigate the mechanism of data attacks causing large physical impacts and quantify the impact and system vulnerability. Finally, this study also sheds light on defense measures and helps in improving the situational awareness. Based on the mechanism revealed, we can perform the risk assessment of the system. For example, pinpointing the critical initial contingencies and determine how we can hinder the spreading of a sequential outage or cascade that is highly prone to the sequential outage attacks. Next section in this paper is impact of false data injection attacks on transmission overloads. This section provides an overview of the plausibility and impacts of an false data injection attack on transmission overloads. First, an overview of the false data injection attack. Here, the integration of communication technologies in smart grids is rendering the system more vulnerable to false data injection attacks. The false data injection attack analyzed in this paper is constructed based on the assumptions. First assumption: the attacker has the system information and can manipulate the reading of meters to inject the false data, and the false data can pass the bad data detection, and thus it can affect the system solutions. Next, the second assumption: the practical false data injection attack, which injects false load data to impact the security constrained economic dispatch. In this paper, the primary reason for using this assumptions is that we aim at performing a worst case analysis to fully reveal the mechanism of sequential outage attack, which quantify its impact and assess the system vulnerability. With the mechanism revealed in this paper, an attacker having incomplete system information may still impose a large impact. The false data injection attack has a risk that it can be implemented as a stealthy attack in which the injected false data may not be prevented by the bad data detection. Next, the false data injection attack induced line overloads. Considering the nature of the problem investigated, the analysis in this paper will be based on DC power flow model. DC models have enough accuracy for thermal overload problems. Even if a DC model may have slightly compromised accuracy as compared to its fully AC version, the attacker can still impose large impact by minimizing the severity index. SOA, induced sequential outages. In this section, we introduce the framework for the sequential outage attacks, induced sequential outages. First, the principle of SOA. Here, we review an important concept, the initial contingency, which is identified as a major triggering event for subsequent failures or even a blackout. An initial contingency was described as a combination of outages that occurs within such a short period of time that corrective action has not been possible before the next one occurs. On this topic, a search algorithm for an initial contingency involving statistically independent branch outages was examined. While the above research highlighted the initiating effect of initial contingencies, but it did not fully investigate the chance of initial contingency occurring. The attacker is able to target at a group of critical branches which forms an initial contingencies in order to leverage the initial contingencies initiating capability, and the judiciously design an optimal false data injection attack to intentionally trigger this initial contingency, which initiates sequential outages or even leads to cascading failures. This is the principle of the sequential outage attack analyzed in this paper. Data flows and control signals under the attack. Figure 1 represents the data flows and the control signal flows under SOA. As shown in the figure, the attacker designs the false data, that is delta Z, and identifies the critical ICs. Delta Z can bypass the bad data detection, so it will affect the solution of security constrained economic dispatch at the control center. When the generators are following the dispatch commands sent from the control center, the target branches will have severe thermal overloads that are enough to cause their outages. Next, illustration of the process of IC identification by the attacker. In the SOA, the attacker's targeted IC can be represented by the intersection of sets 1, 2, and 3. That is the red hatched area in figure 2. Each set in the figure is described as follows. Set 1. A set of ICs triggered by the data attack, representing the direct impact of the attack. Second, a set of ICs that have potentially increased occurrence probabilities, which is referred to as a hidden probability. Third, a set of ICs that has the capability to initiate sequential outages with large system impacts. Here, the attacker can manipulate the intersection of sets 1 and 2 to realize almost 100% occurring chance of his targeted IC, which in this paper is quantified by the flow on each line involved. The IC reaches its overloaded tripping threshold under the attack. So the attacker can target at the initial contingency in the intersection of 1, 2 and 3, which is a weak point of the system. Next, ICs with hidden probabilities. Set 2 in figure 2 represents ICs with hidden probabilities. In this paper, we apply such hidden probability to the IC identification in the attack model. This means that the attacker not only finds ICs that can be triggered and can initiate sequential outages, but also can identify ICs with a potentially high chance of occurring. This corresponds to the intersection of 1, 2 and 3 in figure 2 and indicates a risk that the attacker can identify the IC, which is the system weak point, with even a higher chance of occurring. This helps in performing the worst case analysis and fully revealing the risk of attack and the system vulnerability. Next, physical consequences of the SOA. In this study, we defined two groups of lines for analyzing the IC. The outages of group 1 lines constitute the IC, which is the target of the SOA. Group 2 lines form the early stage of the SOS initiated by the IC, which can be viewed as the direct consequences of the occurring of the initial contingencies. When implementing the sequential outage attack, a smart attacker will try to maintain the network connectivity until the target initial contingency has been successfully triggered, which enhances the stealth of the sequential outage attack. The next section in this paper is mathematical model of SOA. This section presents the mathematical model for analyzing the sequential outage attack. The goal and mechanism of the sequential outage attack. The mechanism of the sequential outage attack, which is illustrated in figure 3. This figure shows how the attacker can implement the attack and maximize the impact. In this, the next thing is implementing the SOA. As shown by the green and blue parts in figure 3, the attacker implements the sequential outage attack by number 1, designing the false data, the green part in figure 3, and number 2, identifying his target IC, the blue part in figure 3. A prominent feature of the sequential outage attack is that the attacker can use the model to implicitly identify the initial contingency, which is a system weak point, at the same time when designing the false data. Here, the initial contingency identification represented in figure 3, the attacker will identify the IC with two features. First, the IC can be triggered by the attack with a potentially high chance of occurring. Next, the IC initiate sequential outages. These two features are realized by the sequential outage attack model based on the mechanism. Next, maximizing the impact. As illustrated by the red part in figure 3, the attacker's ultimate goal is to maximize the physical impact imposed to the system by triggering sequential outages. Next, formulation of the attack model. The sequential outage attack is formulated as a bi-level model represented in figure 4. The upper level constructs the attack, which determines delta T to impact the security constraint economic dispatch SCED in the lower level and identifies the initial contingencies ICs. Based on vector delta T delivered from the upper level, the lower level implements a SCED from the perspective of an operator to dispatch generators based on the corrupted load data and then return the solved P power O to the upper level for calculating the true line flow, that is F suffix S. Next, constructing an optimal SOA. Here, the initial contingency does not necessarily have a fixed number of lines, while which lines will be involved in the initial contingency are determined based on the tripping threshold. Hence, the number of stages can vary when constructing an sequential outage attack. Case study. Simulation settings. The introduced sequential outage attack mechanism is analyzed using experiments on the IEEE 118 bus system. The algorithm is solved by Cplex 12.4 on a 2.4 GHz personal computer with 8 GB RAM. The simulations are conducted in cases 1, 2 and 3 with 9000 megawatts high load level or 10,000 megawatts critical load level as listed in table 2. Simulation results. Case 1. Simulation with 9000 megawatts load and gamma equal to 0.25. In this case, the attacker constructs an optimal sequential outage attack scheme. Here, table 3 to 5 show the results obtained for each iteration. Table 3 includes the megawatt per unit flows and outage sequence in the initial contingency, the outages of group 1 lines, triggered by an attack. Table 4 lists the group 2 lines which are outaged after the attack is accomplished and reflect the impacts of the sequential outages. Table 5 provides the values of the terms and the physical consequences or damages imposed to the system after the tripping of all group 1 and group 2 lines. Case 2. Simulation with 9000 megawatts load and gamma equal to 0.5. This case has the same load level, but gamma is increased to 0.5 in order to see its impact on the risk of sequential outage attack. The results for each iteration are given in tables 6 to 8. In table 6, the initial contingency involves a large number of lines than the initial contingency in case 1, which is primarily due to the increased gamma. Table 7 shows that the initial contingency leads to the outage of a larger number of group 2 lines. In table 8, the objective values indicate that the program stops at iteration 3. Case 3. Simulation with 10,000 megawatts load and gamma equal to 0.25 and 0.5. This case provides a comparative study demonstrating the introduced sequential outage attack during a high load level time period, 10,000 megawatts, while gamma is set at 0.25 and 0.5 respectively. For the two values of gamma, the optimal attacks are both solved as attack, that is iteration 2, which are given in table 9. As compared to tables 3 and 6, large scales of initial contingencies occur in this case, which can be seen from the increased number of outaged lines and the higher line flow levels given in Table 9. Table 10 compares the objective values and the impacts of the sequential outage attack among cases 1 to 3. It can be seen that a higher amount of MSLS and severer system separation will be imposed under such a higher load level. The comparisons in this case confirm a positive correlation between the system load level and the physical consequence imposed by the attacker using an optimal attack scheme. This indicates a greater level of system vulnerability to sequential outage attacks during high load time periods. Clarity of paper. This paper was exceptionally well written. Based on headings and subheadings, it is simple to navigate and retrieve information. Most topics were sufficiently explained with neither excessive detail nor lengthy. Conclusion. This paper reveals a less well investigated system vulnerability under false data injection attacks. The attacker can identify the initial contingency as a system weak point and leverage such weak point to implement the attack and cause large physical damages. The mechanism of the attack is analyzed using a proposed model which quantifies the impact and the system vulnerability. The model can consider the false data injection attack's direct impact on the initial contingencies, the IC's hidden probability risk, and the IC's initiating effect regarding sequential outages. The case studies demonstrate that such attacks can impose serious physical consequences to the system. The proposed model also provides a system risk assessment tool and helps in improving the situational awareness. Future work. Complete simulation on the subsequent propagation of a cascading failure needs future research. It is a part of physical consequences of the sequential outage attack. Next, additional issues will be addressed in future work, such as designing a protection mechanism to stop significant physical damages from such hypothetical cyber attacks. Thank you for watching my research paper presentation.